In this video, we will discuss the fundamental counting principle. There are only two learning objectives. First, to apply the fundamental counting principle to determine the total number of outcomes. And second, continue our work with tree diagrams to represent outcomes for a series of events. You can see the three pieces of vocabulary at the bottom: fundamental counting principle, tree diagram, and factorial. Now, when we're considering the vocabulary, I would like to point a couple things out. You do not have to have the definition for fundamental counting principle memorized word for word. That is not important. You'll note the learning objective does not say know or recite the fundamental counting principle. It's to apply it. So our learning objective is telling us it's more important to know how to use it than to know what it is word for word. Nonetheless, for the sake of completeness, I'll record it now. So there you are. Fundamental counting principle says you can determine the total number of outcomes for a series of events by multiplying the number of outcomes for each individual event. Yeah, that's a lot. That's why we don't expect you to memorize it. Again, knowing how it works is more important than being able to recite the stuff that we have in blue. We also should remember that a tree diagram is nothing more than a tool that you can use to map outcomes. The last vocabulary for factorial, I'm actually going to leave blank for right now. I'll come back to it later on in the lesson and discuss it when it becomes relevant. Continuing our work. A child may choose between milk and juice for breakfast. They may also choose between ham, sausage, and bacon for breakfast. A third choice is to choose between scrambled eggs and sunny-side-up eggs. First, build a tree diagram that shows the different outcomes for what the child might choose for breakfast. This is a part where it's very beneficial to use the fundamental counting principle. Now, don't get me wrong. The directions specifically tell us, build a tree diagram. So we will have to build the tree diagram. There's no way around it. We're told that's what this problem is having us do. But what's helpful is knowing, excuse me, when we get done with our tree diagram, how many branches is it supposed to have? That's where the fundamental counting principle really comes into play. Specifically, the fundamental counting principle would look at it and say, what are the choices that you have to make? The first choice is to make what you're going to have to drink. After choosing what to drink, the child has to choose what kind of meat they want. And then they have to choose what kind of eggs they want. You'll note the series of events. You have the event of picking a drink, and the event of picking meat, and the event of picking eggs. Individually, we could look at each one and say, how many options are there to pick the drink? Just milk and juice, so there are 2 options for the drink. But when we pick the meat, looking at just that, ham, sausage, bacon, there are 3 choices. The fundamental counting principle tells us that if we go build a tree diagram for only drinks and meat, there should be 2 times 3 equals 6 different branches on that tree diagram. And that's if you're doing only drink and only meat together. But there's also eggs, and there are 2 choices for the eggs. The fundamental counting principle will tell us when we build our tree diagram for the 3 things together, 2 times 3 is 6, times the other 2 is 12. Our tree diagram should have 12 branches on it. That's what the fundamental counting principle does for us. Before you do all the work of building the tree diagram, it tells you how many answers should you get. Before you go through all the work of creating the sample space like we did in the previous lesson, the fundamental counting principle will tell you how many should you get. That's its biggest benefit. So let's start our tree diagram. First choice they have to make is the drink. Because there are 2 branches, 2 choices. You would have milk and juice. Note, after they make this choice of what drink to pick, they have to make another choice for the meat. That's why I'm going to put down another dot. You'll note I'm putting the dot down after milk because after you pick milk, you still have to choose between the 3 different kinds of meats. But even if you didn't pick milk and you pick juice on the right, you still have that same choice. You have to pick between the 3 different meats. That's why both milk and juice need to have the 3 dots. Each need to have a dot. And we can then start listing them out. After drink, we had ham, sausage, and bacon. And if you'd gone for juice, you have the same choice. Ham, sausage, or bacon. If you count out how many words I have written out in blue right now, 1, 2, 3, 4, 5, 6, you'll notice what I said before with 2 times 3 equals 6. That's telling us we have what is correct. At level 2, after making 2 choices, we have correctly identified that there are 6 branches on the tree. But we're still not done, because there's still this 3rd choice for the eggs. After every single one of these 6 options that we have listed so far, we're still going to have to make the choice of what kind of eggs. So for each one, you'll note I'm putting down another red dot. And there are 2 options, so each one needs to branch off 2 times. It just so happens that we have the same 2 options for each one. There are scrambled eggs, or there are sunny side up. Scrambled, or sunny side up. Scrambled, or sunny side up. Yeah, I realize this is getting a bit repetitive. I'm betting a lot of people, when they were creating this for their notes, I'm betting a lot of people didn't write out the full word. You really wouldn't need to write out milk. You could just use an M for milk. You could have used a J for juice. I did not do that here because I recognized down the road that having sausage, scramble, and sunny, having 3 S's, could have caused some potential confusion. That would have been pretty easy just to say, I'm going to use a G for, for sausage, use a C for scramble, and like an N or a U for sunny. You can change the letters, that's okay. Just make sure you let people know what they're looking at. Anyhow, coming back, check how many of the red words there are. If we start counting them, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You'll note that's exactly what I said we would get before with 2 times 3 times 2 gave us 12 options. This stuff here that I'm putting inside a little red cloud, We were not asked to do that. We were not asked to use the fundamental counting principle. We were simply asked to build a tree diagram. I did the stuff in the cloud just so that I would know. I wanted to make sure that I knew how many answers there were going to be. I wanted to make sure that I didn't accidentally leave any out or put in too many by duplicating something. By doing a quick 2 times 3 times 2 to get 12, it let me know that at the end, if I wound up with 9 answers, that would tell me I'm missing some. Or if I wound up getting my tree diagram and I could get 14 answers, that's an indicator that I made a mistake and somehow something got duplicated or something went wrong because there were only supposed to be 12. You'll also note this tree diagram got really, really tedious. If you look at level 2 in the blue, ham, sausage, bacon, ham, sausage, bacon. They got just repeated. You look in the red, scramble, sunny, scramble, sunny, scramble, sunny, scramble, sunny, scramble, sunny, scramble, sunny. You keep repeating the same thing over and over and over because at each one of these points, we had to make the same choice. We had the same options over and over and over. That won't be the case for every single tree diagram. Our second example is actually a case where we have that going on. Let's say you're in charge of music for a party and you decide to bring 3 different CDs. You bring Jay-Z, Tupac, and the R.E.Z. Finley Blake. How many different ways could you play all 3 CDs so that each one is played exactly once? Part A asks us, use the counting principle and calculate the number of different outcomes for the order of the music. This one is asking us, if we build the tree diagram, if we create the sample space, how many things should be on it, or how many things should be in the sample space before we do all the work to get it? Well, fairly straightforward to pick that out. We just have 3 spots. The first to get played, the second to get played, and the third to get played. The fundamental counting principle tells us we'll just multiply those 3 particular options. So, for the first CD, how many choices do you have? Well, there are only 3 of them around, so you've got 3. After you play the first one, how many choices do you have for the second CD? Well, I suppose it would be possible you could play the same CD again, but we were told each CD gets played once. Since we're not allowed to replay CDs, that actually tells us we have to subtract one off and have 2 CDs left. And for the third one, then, we're kind of forced into play whatever else we've got left. By the fundamental counting principle, 3 times 2 times 1 equals 6 different orders. In part B, when we create our tree diagram, there should be 6 branches on it when we're done. Now, we don't have much room on this page, so let's go over to part B on this spare page. Keeping in mind that we have Jay-Z to pick from, we have Tupac to pick from, and we have Finley to pick from. So, here's our choice. First CD, what options are available? Well, we could pick Jay-Z, we could pick Tupac, or we could pick Finley. If you pick Jay-Z first, what are your options after that? Well, the only 2 things left were to play Tupac or Finley. We could track this further and say, if you picked Tupac, what choice do you have left for the third one? You can't replay the Jay-Z, you can't replay the Tupac, so the only thing that's left is to say Finley. Now, if you played Finley first, or I'm sorry, if you played Jay-Z first, Finley second, you'll note that tells you you have to play Tupac last. I'm going to come over to the Tupac branch now. If Tupac was picked first, What choices do you have for the second CD? Well, there are two choices, so that will branch off being either Jay-Z or Finley. If you pick Tupac then Jay-Z, you're stuck with Finley for the third. But if you pick Tupac then Finley, you'd be stuck with Jay-Z for the third. Moving to our next branch. After Finley, we would have the options of Tupac or Jay-Z. But if we pick Tupac as the second CD, so Jay-Z for the third, and vice versa, there. Count the total number of branches in the red. 1, 2, 3, 4, 5, 6. That matches the fundamental counting principle. We figured using the fundamental counting principle that we should have 6 branches. We actually have that, so we're totally set. Coming back to part C now. Construct the sample space that shows all the different orders that the CDs might play. And there are several different correct ways we can do this. You can use logic to just think through it. You could use a tree diagram to think through it. There are pretty much any way you want. You just have to create the list of all the 6 different methods. All the 6 different orders that you can get it. Well, since I already have the tree diagram, I'm going to take advantage of that and follow the different branches. One branch is to say Jay-Z first, then Tupac, then Finley. Well, I can put that in an order. Jay-Z, Tupac, Finley. But I could have branched off and done it a different way with Jay-Z first, Finley second, Tupac third. That's another order where I could have had Jay-Z, Finley, and Tupac. You notice how now leading down to the red, that entire path on the left is all colored in with the same yellow? That tells me I've used up everything down here. By already reaching these other options, that part of the tree is finished. And I need to go on to the next part. So I could say, and I'm going to switch this one to kind of this greenish color because I didn't get to use that yet. I could have Tupac be first, followed by Jay-Z, followed by Finley. So Tupac, Jay-Z, Finley. Following the same end line, Tupac, Finley, Jay-Z. And all the paths leading down to these ones are filled in, letting me know that branch is done. Now I'll have to go back off to this end, and I'm switching to purple here. So I'd have Finley, Tupac, Jay-Z, and Finley, Jay-Z, Tupac. Please note then that we have colored in all the different paths that lead down to the red, and so that covers up our entire sample space. We know then to finish this problem, sample spaces always have these curly brackets. Curly brackets means it's a set, and so we can say, using our complete sentences, the sample space for playing the 3 CDs is that. And we're done. Completely finished with this problem. But please note, we had 6 items in the sample space, which matched the 6 branches of the tree diagram, which matched what we had for the fundamental counting principle. That's where our first learning objective is coming into play. Apply the fundamental counting principle to determine the total number of outcomes. We were doing that with 3 times 2. We were doing that with the 2 times 3 times 2, each of those components was using the fundamental counting principle. For example 3, you're playing Blackjack. And in Blackjack, you are dealt 2 cards from a standard deck of 52. Now, if you're a person who has not played cards much before, you may not be familiar with what the standard deck is. A standard deck has 4 suits. Those suits are clubs, spades, hearts, and diamonds. Within each of the 4 suits, there are 13 cards. They have the ace, which may be thought of as a 1. So it goes ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the 3 face cards, jack, queen, and king. Each suit is 4. There are 4 suits, 13 each. 13 times 4 is how you get your 52. Now for this one, we are asked, how many different outcomes are there when you're being dealt 2 cards? In this instance, we're considering every single card to be a different possible outcome. And so if we wanted to, we could create a tree diagram here. We could say, for card number 1, I have 52 branches. And you can already see, go ahead, start doing this with 52 branches and see how fun that's going to get. But at the end of all 52 of those branches, you have to have another choice for card number 2. And they're going to have to branch off a crap load for every single other card. And you can see, yes, it would be possible to do this tree diagram, but this would be absolutely massive. It would be so big. There's no way you would want to do it that way. You don't want that whole list. It would take a really, really long time to create that by hand. And this is where the fundamental counting principle is so incredibly powerful. Because when we're doing the fundamental counting principle, all we have to look at is see this piece. We are dealt 2 cards. Because there are 2 cards, we just have to consider 2 slots. The first card and the second card. So I can put down a line for each. If I can figure out how many cards are available for the first and how many cards are available for the second, all I have to do is multiply those 2 numbers and I will get my answer. So what are they then? How many cards could you possibly be dealt first? Well, in this one, there are 52 different cards. So we regard it as 52 different options. Now, just for the sake of argument, let's suppose that you were dealt the 4 of hearts. After the 4 of hearts has been dealt, how many cards are left? How many different options are still available? There are still 51. Thus, according to the fundamental counting principle, if we want to answer this question, all we have to do is take 52 times 51. We multiply those 2 numbers and we have our answer. So let's crunch the numbers. 2 times 1, 1 times 5, automatic 0. 2 times 5 is 10, carries that over to get 26. And so when we add them up, we get 2652. And so there we go, 2,652. To write this up with our complete sentences, there are 2,652 different hands when dealt from a standard deck. In Blackjack. Not the most eloquent way to phrase that sentence, but it gets the job done. Kind of a lot when you think about it. 2,652 different ways that you could play. Or just to start, that's not even finishing. Example 4. How many different 10-digit phone numbers could possibly be in North Dakota? Please keep in mind, in North Dakota, all phone numbers are required to start with the first three digits 701. We're not asking for a tree diagram. We're not asking for a sample space. Because frankly, do you want to list out every possible phone number that there could be? It would take days. Well, fortunately for us, we can recognize we're talking about a 10-digit phone number. So we have the first number, second number, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. We could start filling them in and just start guessing, but let's consider these options. Let's start thinking about the criteria. We're told that it does have to be North Dakota. So in North Dakota, these first three numbers have to be a 701. Please note, that does not mean that there are 7 options. I'm not saying the 7s, 0, and 1 are going down here. I'm not saying that. I'm saying, since it has to be a 7 here, how many options are available for that? There is only one option. The only number that is allowed is the 7. So there's one choice. And when you go to the second number, how many different choices do you have available? How many different things might it be? Again, since we're forced to be in North Dakota, only the 0 can work. We have only one option. It must be the 0. And same thing for the third number. It must be a 1, so there's only a single choice. After that is where things get a little bit more interesting. From here, in the fourth number, how many options are there? Well, we could have a 1, 2, 3, 4, 5, 6, 7, 8, 9. And a lot of students make this mistake of saying there are 9 choices available because they think of 1 through 9. They tend to forget sometimes there's also the digit 0 you could use. So when you factor in 0, there are actually 10 numbers that you can pick from. And when you go to digit number 5, how many choices are there to pick from? Well, let's say we had a number 701, 6, 2, 7, 36, 12. I don't know what that number is, but there we go. Are we allowed to repeat numbers that we already had? Yeah, for cell phone numbers, we know it's okay to repeat. For example, this one has a 7 get repeated. It has a 1 getting repeated. And there's a 2 getting repeated. So yeah, we have a bunch of numbers that are getting repeated. Oh, I just noticed there's also a 6 getting repeated. So yeah, in this one, it's plenty fine. It's okay to repeat numbers for phone numbers. And so we don't lose anything. There are still 10 more choices. And 10 more choices, and 10 more, and 10 more. Every single digit has 10 potential options. Well, now that we've been able to fill in all of the 10 different slots for the 10 different digits, just multiply it out. What number is 1 times 1 times 1 times 10 times 10 times 10 times 10 times 10 times 10 times 10? Well, I'm just going to take a quick piece and say, count the zeros. 1, 2, 3, 4, 5, 6, 7 zeros. So 1, 2, 3, 4, 5, 6, 7. Taking advantage of some of the shortcuts that we had before. And there we go. There are 10 million different phone numbers that are available in North Dakota. And given that there are only about 675,000 people, it's actually possible that every single person in the state, including babies, could have 10 different phone numbers and we'd still have a lot left over. Problem B is pretty similar. How many different numbers can be in North Dakota? But we have some added restrictions. Now we're putting in the restriction that it's still a North Dakota number, but we are putting in the restriction that it does not start with a 4 and does not end with a 3. So let's start considering these different pieces. So putting in the restrictions, here's what we have to have. The first three numbers have to be 701, and this one has to be not 4. And at the end, it cannot end in a 3. With those restrictions, what are the options? What's available? Well, in the first slot, it has to be a 7, and it has to be not 4. How many numbers fit that bill? Just a single one. It has to be the 7, and since 7 is not 4, we have a single choice. Like last time for the 0 and the 1, there are single choices. At the very, very end, for not a 3, there are 9 numbers that are not 3 for single digits. And for everything else, there are 10s. So let's multiply it out. 1 times 1 times 10 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 times 9. And there we go. There are 9 million phone numbers in North Dakota that meet the criteria. Just for the sake of argument, I would like to consider a fictitious Part C that gets rid of this word don't. How many numbers are there that start with a 4 and don't end in a 3? Well, basically all these pieces are going to be the same. Down at the end, not 3 still has 9. All these blank ones are still 10, but where we get into trouble then is up here at the beginning, because it says it must be a 4 to start. But because it's North Dakota, it must be a 7. So how many numbers are there that are both a 4 and a 7? Not a 1. There are 0. So go ahead and take 0 times 1 times 1 times 10, 10, 10, 10, 9. The short version is because you're taking times 0, that completely wipes out the whole thing. There are 0 numbers for our fictional Part C that must start with a 4 in North Dakota. They just don't happen. In another state, that could be okay, but not here. Please note, again, this is the fundamental counting principle. The whole purpose of this is to figure out how many different options would there be, how many different outcomes would there be, without actually needing to create a tree diagram, which in this problem, do you want a tree diagram with 10 million branches? Of course not. Okay, this one, suppose you have 5 assignments on the ICU list, and for 5 different classes. You have math, English, science, history, and PE. In how many different orders can you do all your work on the ICU list? We could create a tree diagram. Completely valid strategy. We could create the whole list, but that's going to be a fair amount of work, and we don't need the whole list. We were not asked to list all the orders. We were not asked to create a tree diagram for those orders. We just said how many. And that's a lot easier, because we can go through and say, we have the first assignment, the second assignment, third assignment, the fourth assignment, and then the last one you've got on the list. We can keep track and then say, multiply them all out. Well, as of right now, how many different assignments are there? You have 5, so you've got a choice between the 5 that you will pick. Let's suppose you pick to get rid of science first. Now that science is gone, how many choices do you have left for the second option, for the second assignment to do? Now, there are only 4 left. So suppose you chose to get rid of your English second. How many choices are left for the third assignment? You could pick 3 of them. Supposing you got your math done next, for the fourth assignment, how many are left or picked from? There are 2. And so let's say you pick to do history. At this point, there's only the last one. The only thing you could pick now is to do your PE, which gets rid of everything from your list. By the fundamental counting principle, all we have to do is take 5 times 4 times 3 times 2 times 1, which gives us 120. I would like to point something else out here. We have the answer of 120. That finishes the problem. That's awesome. But I'd like you to notice the pattern in the numbers. 5, 4, 3, 2, 1. How you're just counting backwards. When you do this, where you count backwards and multiply, that was our last vocabulary word. That is a factorial. Going back to the beginning, where we had the vocab, a factorial is when you count backwards until you get to 1, and you multiply all the numbers along the way. The notation we use for it is an exclamation point. So, for example, if we had 5 factorial, the exclamation point is red factorial. That says count backwards 5, 4, 3, 2, 1, and you multiply them all out along the way. I'm going to pull up a scientific calculator here, and we could note right here, 5 times 4 times 3 times 2 times 1 equals 120. We had our answer. Coming back, we could say, let's do 7 factorial. That one is 7, 6, 5, 4, 3, 2, 1. And we could go back to the calculator to save some time, because these things are so big you don't really want to do them all by hand. It's just really time consuming. So we could say 7, 6, 5, 4, 3, 2, 1 equals, and we have our answer 5,040. I should write down this one in the yellow of 120. Now imagine for a second that we have a third one of 20 factorial. Well, counting backwards, 20, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. That was a lot of talking, and that would be even more multiplying. Let's go to our calculator to do it. 20 times 19 times 18 times 17 times 16 times 15 times 14 times 13 times... Did you catch what I just did? If you haven't seen it, 20, 19, 18, 17, 16, 15, 14... You notice how I almost skipped the 13? When you're going over these things really quickly, it's pretty easy to make a mistake just because you're trying to get it done so fast that it's easy to skip a number. It's easy to accidentally type some number in wrong. And so you do have to be careful when working with these pieces. 7, 6, 5, 4, 3, 2, like this. You see how I have 21 at the end instead of 2 times 1? That would, of course, change the answer. You've got to be careful about things like that. And so when I hit equals, here we go. 2, 4, 3, 2, 9. 2, 4, 3, 2, 9. And then it was a double 0. Nope, it was 0, 2, 0, 0, 8. 0, 2, 0, 0, 8. 1766 4000. And was there another one? Yeah, one more 0. So there we go. There. So, woo, huge number that took forever, even with the calculator. Fortunately, this calculator has a very nice shortcut attached to it. I would like to point out where I found this one. If you do just a quick Google search for scientific calculator, it will pull up this piece. I don't want to use this one. I actually went to the next one, this Web 2.0 scientific calculator. That's a free one that I was using here. Take a look at the bottom left part of this calculator. Do you see this button that has an exclamation point in the bottom left? In the very bottom corner, you have the buttons NCR, NPR, then the exclamation point. That's the factorial button. You can get these answers a lot quicker. You see how 5 factorial we multiplied out to get 120? You could type it into your calculator, 5 factorial equals, and right up above it in the white, we have 120. We also looked at 7 factorial equals 5040, which matches exactly what we had in the red. Where that gets to be really nice is with numbers like 20 factorial, because that eliminates the possibility that you might mess up with times 19, times 18, times 12 and accidentally skip numbers or accidentally miss a multiply sign. You hit equals, and there we go. 2432902008176640000. Look familiar? There we go. Nice little time saver. Remind you of our learning objectives. First, apply the fundamental counting principle to determine the total number of outcomes. And second, use tree diagrams to create or represent the outcomes for a series of events. That includes problems where you have a bunch of repetition in your tree diagram, or there is not repetition in the tree diagram like the CD problem. In any case, whether you're doing a tree diagram or trying to create a sample space or just try to answer the question, in any instance, you can use the fundamental counting principle to determine the total number of outcomes, and all you have to do is multiply by the number of outcomes available at each particular stage.